gave a lecture about batteries in Crawley College. Yeah. But actually, I started working on hydrogen earlier than battery. And I think, yeah, just now talking to one of the friends here was the reason that I moved kind of to battery, also creating another research line was because back to 10 years ago, the UK government decided that hydrogen was not important and decided to invest heavily into batteries. And as an academic, I had to adapt. So I diversified my research to batteries. But good news is a few years ago, the government decided that hydrogen can play a very important role. So there's a lot going on now, which is very exciting. And I want to show this because this is my personal drawing showing how the human society over the past probably 100 years, the past century, how the power source, the fuel, has evolved. So we started with coal, the steam engine, the dirty steam engine, and also the coal-fired power plant, powering transport and also electricity supply. And it created a lot of problem. There's a huge amount of CO2 emission. I think the foggy London back to, was it 1960 or 70, was part of that. And it moved gradually to hydrocarbon, heavy hydrocarbon fuels that include petrol, diesel, and we use this to power our cars and also some combustion engines. And then gradually moving to light hydrocarbons, methane, natural gas, and propane, C3H8. And you can see we have more and more hydrogen coming and less carbon in the fuel. So my hypothesis was that in the future, we can probably completely remove carbon in the fuel, and then we only have hydrogen left. Another chemical coming to play, which is ammonia, that I will mention later why we want this chemical to come into play. So all this development is in the context of the world coming to realize that we want to decarbonize a lot of stuff, to carbonize transport, electricity supply, heating system, industry, chemical production, etc. In order to meet that temperature target, to control the temperature rise below 1.5 degrees. And there's agreement to phase out the fossil fuels and the coal. So there's a lot of development of batteries in response to that, but I will show that there are some things that battery cannot do. So hydrogen can come into play. Okay, and so back to 5 years ago, the government set this 10-point plan where point 2 was to drive the growth of low-carbon hydrogen. And there you can see that there's a very ambitious aim to develop 5 gigawatts of low-carbon hydrogen production capacity by 2030. I think we are still far below that. And there's a lot of funding now being put into companies and also research trying to develop that capacity. So in that context, the UK government, the Research Council decided to fund this UK hub for research challenges in hydrogen and alternative liquid fuel, and I got involved into this. And the aim was to develop hydrogen-based technologies, including hydrogen production, led by Professor John Irvine at St. Andrew University, and then hydrogen storage and distribution led by Professor Tim May, and use. So I'm looking after that, and alternative liquid fuel, mainly ammonia, because we decided to focus on zero carbon fuel instead of fuels that containing carbon, and ammonia become a promising candidate for that. But of course, to develop hydrogen, it's not so simple, because there's a lot of things. There's a public rejection, and or misconcept, or etc. There's probably not very good public acceptance. So we need to. Chris Jones led the study onto how to make social acceptance, to make higher social acceptance, and then Paul Dose at UCL led the economic theme, trying to look at what kind of economic models we should develop in order to facilitate the adoption of hydrogen technologies, and of course the environmental impact of hydrogen technologies, and finally, but most also very important, safety is very important. So we got actually 10.7 million funds from Research Council, not a lot. The 4.1 million is used as a flexible fund, meaning that we can still bring more people in. So the first call, we funded 10 projects, which started early this year. And then there are a lot of support from university partners to fund PhD students to, because this is really not a lot. So if we look at US or Germany, they are probably 10 times or 20 times funding than we have here. It's supposed to be as a multidisciplinary hub. You can see the nature of the work we're doing is really multidisciplinary. So there are a lot of, so these are the funding university partners, and with the flexible call, we now got much more university coming in, including University of Glasgow, Newcastle, Birmingham, I think University of Dundee, and other universities. So what is hydrogen? Let's have a look. Hydrogen is the #1 element in the periodic table. This is hydrogen, and normally it exists as hydrogen molecules, having a covalent bond between the two atoms. There are some very unique properties of hydrogen that we should look at. So similar to other matters, it can have solid, liquid, and gas phase. But the challenge with hydrogen is it only becomes liquid at this low temperature. That's a very, very low temperature. That means most of the conditions exist as gas. And because it's so light, it can go everywhere. And it means that if you look at the density here, of course, when it becomes solid, the density is higher. Liquid also density quite high. And when it's in the gas state, the density is very low. So that means if we want to store it, we have to, if we want to store it at high density, we have to make it into liquid and make it at this low temperature, meaning a lot of energy have to put into to make it as a liquid. So that's the challenge, which I will come back later. Another challenge is it can be very flammable. Once the concentration, the volume fraction of hydrogen in air reach 4%. Yeah, it's a very low percentage. So that's why hydrogen is very easy to be flammable, because it can be ignited at such a low concentration, and then up to 75%. This is too much hydrogen and too low hydrogen. That's unlikely ignition will happen. So bear those in mind. We will come back to those points later. Now, traditionally, we thought there's no hydrogen in nature. hydrogen didn't exist in nature. This has been modified by the discovery of the so-called white hydrogen, the naturally occurred hydrogen, which was discovered, I think, 37 years ago. At the time, the significance was not recognized, but now I think some companies are thinking to dig up that hydrogen, although it's very challenging, and the UK haven't discovered any hydrogen mines. It's mainly in US, France, I think, Europe, Australia. But it's deep under the crust. Yeah, it's where the rock become liquid. So it's not very easy to get that hydrogen out. Therefore, there's still a lot of development try to produce hydrogen from different sources. So the first one is by coal, gasification of coal, producing hydrogen and CO2. And CO2, we know CO2 is a greenhouse gas. And gray hydrogen is by steam methane reforming of, steam reforming of methane or the fossil fuels, again, producing hydrogen and CO2. If we capture that CO2, store it, then it's called blue hydrogen. The turquoise hydrogen use a different method. It's called pyrolysis. Basically, it's to split natural gas, methane, into carbon and hydrogen. So you don't produce CO2 in that case. The yellow hydrogen is when you use photocatalysis. So you use the solar energy to split water. And it's considered very clean. The purple hydrogen is when we use nuclear power as an electricity input to split water. And the green hydrogen is when we use renewable from solar and wind power as electricity input. So I'm going to now briefly introduce the main types of hydrogen production method. So the first type is the thermochemical method. I'm using very simple illustration here. So basically we can have coal or hydrocarbon or biomass as input into this reactor. You can see very high temperature and pressure, and we can either input high temperature steam, so we do the steam reforming reaction, or we input air, we do the oxidation reaction. Then we produce hydrogen and the CO. And that gas mixture then goes through another reaction called gas shift reaction, water gas shift reaction, to further convert CO into CO2. Again, you need to input steam or air, high temperature and high pressure. And after that, so coming from this, depending on how if you remove CO2, then you get blue hydrogen. If you don't, then you get gray hydrogen. So it looks very simple, but however, the reality is more complex. So this is taken from a PhD thesis that I examined at the University of Sheffield, trying to develop a chemical process, starting from input natural gas to produce hydrogen and CO2, and then do the CO2 removal. So it requires a lot of units coming into play. This is chemical engineering. And he did some calculation about energy consumption by using different CO2 absorber. And you can see that when we add, so the yellow bit is when we add carbon capture to make blue hydrogen. When we add carbon capture, it actually adds a lot of energy consumption. While the production of hydrogen without CO2 capture already consumes a lot of hydrogen, but adding CO2 capture consumes a lot more energy. And the total annual cost, that includes the annual capital cost, the blue part, and the annual operation and maintenance cost, the orange part, is also very high. So producing blue hydrogen by integrating the carbon capture with hydrogen production is very both energy intensive and very expensive. Another method is also based on thermochemical principle, but using hydrolysis, as I mentioned just now. You can input typically natural gas or biomass. So there's quite a lot of development within the UK and also in other countries trying to do this reaction. So without any input of air or steam, yeah, just do this in an inert condition, do the high temperature pyrolysis at high pressure at an inert condition. By doing this way, you actually, you try to get hydrogen from the molecule, and then you get either carbon or bio-oil. So this could be quite promising because then you don't produce CO2. So this is called turquoise hydrogen with a valuable byproduct. But looking at that temperature and the pressure, and also the condition it's not going to be easy. Yeah, inert condition. You have to realize that inert condition. But yeah, it could be promising. Another way is the photocatalysis method. So this is very sustainable because you can just use the photons from sunlight, and then you kind of stimulate some holes, turn some holes, so do some conversion of holes into electron. I'm not a physicist, but I think some of you are better than me in understanding this. And this electron then can do the reaction to split water into hydrogen and oxygen. So you use a semiconductor to do that. I'm citing this paper published a few years ago, but they try to load those semiconductor catalysts onto a wood structure where you have this cellular structure, and they obtained quite high performance comparing to many other reported performance. But even so, you can see the hydrogen production rate, macromole per hour per centimeter square. So that's 10 to the minus 6 macromole. And so that means the hydrogen production rate is very, very low. Probably not enough to meet our demand. Yeah, so there's still a lot of research. Having said that, there's still a lot of research trying to improve this. And if there's a significant breakthrough, maybe, this could become viable. But at the moment, the production rate is too low. So the most promising method is by using electrolyzer. So this is an electrolyzer. It's quite similar to a battery. It's an electrochemical device where you have two electrodes. So there will be two separate reactions here. One reaction gives you hydrogen, one reaction gives you oxygen, and then you have electrolyte in the middle, and then you input electricity. So the idea is if we get electricity from either solar, wind, even nuclear or geothermal, then we could have sustainable hydrogen production. And the efficiency of this device normally 60 to 70%. Yeah, so you can have very decent hydrogen production rate. Now there are different types of electrolyzers. The first type, which was invented many years ago, I think it was probably even maybe more than 150 years ago, alkaline electrolyzer. This use alkaline media, so potassium hydroxide, highly alkaline. And because of this alkaline environment, it enables us to use non-precious metals for catalyzing the reaction, such as nickel. And in the middle, you have a porous material called zircon to separate the two electrodes. So you have, as I say, separate reactions happening here. You want the transportation of hydroxide ion from one electrode to the other. It typically operates 60 to 100 degrees C. and voltage this range at this kind of current density, and lifetime can already reach above 100,000 hours. It's the most mature electrolyzer. There are a number of companies trying to commercialize this, and in recent years, there's a lot Chinese companies trying to move into this technology because the technical barrier is not so high. If you look at those materials here. The downside is the current density is not high enough, as I will compare to other technologies like this one. So the proton exchange membrane electrolyzer, which use a proton exchange membrane sitting in the middle to separate the two electrodes and allow hydrogen ion to move from one electrode to the other. So the separate reaction at each electrode is now different from the alkaline electrolyzer, but the overall reaction is the same. Oh, sorry, I think I got the, it should be the other way around, water to hydrogen and oxygen. However, the problem is because it's an acidic environment, so we must use highly corrosive resistant, corrosion resistant precious metal as catalyst, such as platinum and iridium oxide. Those are very, very expensive material. That means this type of electrolyzer is very expensive. Temperature about similar to alkaline electrolyzer, and you can see that we can reach much higher current density. That means the hydrogen production rate is going to be much higher than the alkaline electrolyzer, and the voltage is not so high compared to alkaline electrolyzer. There's a Norwegian company called Now. They have managed to achieve very long lifetime, and particularly so we have ITM Power, which is a UK-based company based in Sheffield. So already commercializing this electrolyzer, doing very well. Another type is called anion exchange membrane electrolyzer. So basically, it's used the idea of alkaline electrolyzer, creating an alkaline environment to enable us to use non-precious metal catalyst, cheaper, but instead of using a polar separator, now it uses very thin membrane, probably 100 micrometer thick. And this, the benefit of this is now the internal resistance now become much lower, so you can then operate at a higher current density and high voltage. So you can see in terms of current density and the voltage, it's comparable to the PEM electrolyzer, but lifetime is still a challenge. So this is the current challenge, and there's an Australian company, a German company, and Canadian companies, but I don't think there's a UK company at the moment working on this technology. Another one called solid oxide electrolyzer. So I want to say that both alkaline electrolyzer and PEM electrolyzer now have reached commercialization. You can buy them from market. But anion exchange membrane, you can buy it from the Inactor, a German company. I think they won the prize from King Charles, some kind of prize, 2 years ago. This one is still under development. It's called solid oxide electrolyzer. By the name, you can imagine that most of the material here are ceramic material, which allow the conduction of oxygen ion. So these are the typical materials: nickel mixed with gadolinium doped cerium oxide, and yttrium stabilized begonia. So all of them are ceramic material. And because of that, again, I think I got the overall direction wrong. Apologize for that. And because of that, you have to operate at high temperature because the conduction of oxygen ion is more active at high temperature. So typically, this has to be operated at 600 to 1000 degrees C. and very, very high temperature. And because of that, you have thermodynamically, you can get very low voltage at this high current density. So the benefit of this is you get high efficiency. But then the challenge is to maintain that high temperature. So this is a German company, and Denmark company, US company, UK company based in Horsham, and they now have a branch in Redhill. We are collaborating with them to develop this electrolyzer technology. So if we look at the cost of the PEM electrolyzer, you can see 45% of it is due to the material you used in making this electrolyzer, porous transport layer, bipolar plates, catalyst, but also you have some costs to do with power supply. You have to get very pure water, and you have to process the hydrogen and get compressed, etc., get cooling, etc. At the moment, the cost of hydrogen production is nearly $5 per kilogram hydrogen. The Department of Energy, the US Department of Energy, set target to say that if we want to reach widespread application for hydrogen, ideally we want the cost at $1 per kilogram of hydrogen. And to do that, so they did some analysis that you can actually, if we get 80% of reduction in electrolyzer cost, we can bring that cost down to $3. But electricity cost is also a big part, so we can, if we bring that electricity cost down, we can further bring the cost down. And electrolyzer efficiency, if we can improve the efficiency to 76%, for example, then we can bring that nearly $1. And then, lifetime, so efficiency, lifetime, cost, the three factors here, apart from electricity, that's maybe something that we are not able to control. If we want to develop electrolyzer technology, we need to bring the costs down and make them last longer and improve the efficiency. So that's the target. Hopefully, we will make a progress on that. So based on this, this paper nicely map out how we can use hydrogen. We can use it to heat up the building or doing cooking by pumping some hydrogen into the gas grid. This is still under debate. Not all the people agree with that. There's a regulation, EU regulation, to set the limit amount of hydrogen that you can put in the gas grid. I think in the Europe they are now trying to do that, but I think the UK still haven't opened that possibility. So we can also use them in cars, powering passenger cars, buses, trains, and trucks. At the moment, because the battery has been developed so well, so the common sense is that probably for passenger cars, batteries would be better than hydrogen. But for buses, heavy trucks, and trains, probably hydrogen can, because then it becomes very heavy for batteries to be put on those vehicles, and then hydrogen can probably last longer. And we can also use hydrogen to synthesize fuels, including methanol, ammonia, or sustainable aviation fuels. We need hydrogen to do that. And once we have the fuels, then we can put them also into aviation and shipping. And also another application of hydrogen is for refining of petrochemicals, steel production, chemical production. At the moment, actually, most of the hydrogen being used nowadays is for production of chemicals. 60% of hydrogen being used nowadays is for chemical productions. This people haven't realized actually. We use a lot of hydrogen in chemical production, and that includes petroleum refining, methanol production, production of electronics, and ammonia production. I will come back to that later. Metal production and fabrication, food processing, and cosmetics. So if we want to decarbonize those sectors, we also need to decarbonize the production of hydrogen so as I said, the most promising is by electrolysis of water with electricity coming from renewable energies. So just to show some showcase of some applications. So this is when we use a fuel cell. So we can use hydrogen to supply a fuel cell to generate electricity and use that to power a lot of things. And those are some examples. So trains, trucks. This is a UK company, River Simple Airbus, Toyota bus, and marine applications. These are already being used, applied. The UK actually has a very strong base in fuel cell technologies. Over the past, I think 3 decades, there has been a lot of research into fuel cells. So those are the companies working on fuel cells in the UK. Very strong in terms of internationally. Another application of fuel cells is for this so-called distributed energy generation. So the idea is, so this is a conventional electricity supply where the electricity is generated in a coal-fired power plant far away from residential area. Then you transmit through the transmission lines. Then you lost. So you throughout this process. If we start 100% at the beginning, then we only got 35% delivered to the house. But if we use a fuel cell in a house, or near a house, we can generate electricity. We only have then 10% of loss. We deliver 90% of the energy into our house. So there's a lot of development now in Japan and South Korea. They are building those demonstration in towns, small villages and small towns by using this idea, the distributed energy generation. So we've talked about the different types of hydrogen production technologies and different hydrogen application areas, but it's limited by hydrogen storage. Hydrogen storage is the bottleneck. I'm trying to illustrate using this drawing. The reason is, okay, so if we look at 1 kilogram of hydrogen stored at different conditions, so this is the kind of volume we require to store 1 kilogram of hydrogen at a normal temperature and pressure. And if we increase the pressure to 700 bar, we decrease the volume to 24 liters, but it's still quite a lot. And if we make the hydrogen into liquid, volume become 14 liters. But as I say, liquefied hydrogen can only happen at minus 253 degrees C. So it's a lot of energy required and very energy intensive. Typically, I think now the most common way is compressed hydrogen at 350 to 700 bar in a tank. Another method is to use material-based. So you make the hydrogen, you store the hydrogen in some kind of solid materials. There are a lot of different materials here, which I will give a bit more detail. So we have this physical method. We store in compressed cylinders and liquefied hydrogen. For both of these, options have been criticized in terms of safety. Transporting long distance is not ideal. And we've done some safety studies on hydrogen. It's, as we mentioned earlier, it's easy to go to the combustion reaction. So if you have leakage of hydrogen, then it becomes a tricky situation. So that's why, within the hub, we now have some project working on hydrogen sensors to detect hydrogen leakage. And there's a Polymath University studying the liquid hydrogen, trying to use it for aircraft application. Or you can do it on pipeline, but you need to modify the pipeline because currently the pipeline is not very suited for transporting hydrogen. Or you can use adsorptive hydrogen, meaning that you put some porous material in the cylinder, in the tank. So you probably store it at a much mild pressure, but the molecules can be stored in the porous material, so at a reduced pressure. The chemical method includes including storing hydrogen in a metal hydride, such as magnesium hydride, but very heavy, and then liquid organic hydrogen carrier, ammonia, methanol. So for all of this, you have to have then a second step to crack the hydrogen out. So adding the cost. So why ammonia? If we look at this diagram, you can see it map out the volumetric hydrogen density and the gravimetric hydrogen density for different hydrogen storage media. And liquid hydrogen is here. It has probably the highest gravimetric hydrogen density, but the volumetric is still not very high. Well, it's quite high, but as I say, you need a huge amount of energy to do the liquefaction and to carefully manage that liquefied tank. It's not very easy. And ammonia is sitting here. You can see that even at a very mild condition, so 1 megapascal and room temperature, it becomes liquid, and both the gravimetric density and volumetric density are very good. So ammonia becomes liquid at either minus 33 degrees C or under atmospheric pressure, or room temperature and a pressure of 7.5 bar. So you can easily liquefy them, and there's already a large infrastructure related to fertilizer industry. So it's easy to store and transport, and there's established production and transport infrastructure, and it's zero carbon. So you don't have CO2 emission from that. So that's why recently there has been a lot of interest into ammonia, and I want to show here is this famous Haber-Bosch process invented by two German chemists, Haber, who developed this in lab, and Bosch, who scaled up for production, large-scale production. So high temperature and high pressure, and this has been, over the past 100 years, this has been widely adopted for ammonia production. And there's a number of large-scale ammonia production plants in the world, typically producing 2,000 to 3,000 tons of ammonia per day. And you can transport it through established pipelines and ammonia. I think in US, Russia, they have hundreds of kilometers of pipelines for transporting ammonia. And currently, 80% of ammonia is used for fertilizers. And then the rest are being used for making polymer materials, dyes, explosives. So if we want to use ammonia as a hydrogen carrier, we need to be careful then we don't compete with agriculture sector, because fertilizer is very important for our food. So that's why there has been now quite a lot of research trying to develop alternative methods, low carbon or zero carbon alternative method for producing ammonia. So this is the conventional method, Haber-Bosch, using nitrogen from air and hydrogen from methane to produce ammonia. So one idea is that instead of taking hydrogen from the methane reforming, we could take hydrogen from water electrolysis, and then you can decarbonize this process. Yeah, you can produce so-called low carbon ammonia, but still the Haber-Bosch process requires high temperature and high pressure. And this Denmark company, Topsoe, they already demonstrate this idea based on this idea. So using solid oxide electrolyzer, producing hydrogen, and input with Haber-Bosch, and combined with nitrogen to produce ammonia. Another, more probably radical idea is we just input water and nitrogen, and we make the reaction within an electrolyzer. So you just have electricity input, and then you produce ammonia. So this currently this is probably the most promising route, but it's still in research. The production rate is still very low at the moment. So we need a breakthrough in that. So with that, I want to show some research being carried out with some collaborators. So Oxford, Dr. Bingjian Nie's group, he kindly shared the slides with me. So they work on an alternative method called chemical looping, based on ammonia synthesis. So by using lithium hydride as a mediator to produce hydrogen. And by using this method, they can synthesize ammonia at a very low pressure. That's the advantage. Now, there are, as we mentioned just now, hydrogen can be used in a lot of different areas, transportation and chemical production. But there's some other sectors like steel making and high temperature industry. These are very difficult to be electrified because typically they require high temperature operation, and typically for steel making, this process called iron ore reduction to get us iron. You have to put some reducing agents there, and traditionally they use coal to do the reduction reaction, and of course it produces a lot of CO2, and at the moment the 11% of the global CO2 emission comes from steel industry because of that, mainly because of that. And the idea is that if we could replace the coal, some of the coal with hydrogen, or replace the coal completely, the majority of the coal with hydrogen, then we can get much less CO2 emission from that. We still need some kind of carbon to make steel, right? We need a carbon content in steel. So you still have some coal there. And again, I think a Chinese steel company called BioSteel already demonstrated this, and this is a work by a South Korea company. And again, within the hub, with Dr. Bingjian Nie's group at Oxford, they are trying to use hydrogen and also ammonia to do the direct reduction of iron ore. And of course, the ammonia direct reduction is still under research. So hopefully we will make that viable. Other applications of using hydrogen and ammonia include Portland cement production, because this operates at a very high temperature. Glass production, again, very high temperature. So the idea is to use the combustion of hydrogen and ammonia to produce that heat needed for that high temperature. And this is a demonstration. This has been successful. This is with the so-called China's Hydrogen Valley in near Guangzhou, not very far from Hong Kong. I visited their lab last year. So they published paper, and yeah, when I visited them, they also showed me the product, the ceramic product. They use pure ammonia combustion to provide the heat for ceramic production, and they showed very low NOx emission, stable and complete combustion, and good quality of ceramic produced. Showing viable, some possibility of using ammonia to produce to provide heat for those high temperature industry where electricity would be quite difficult. But it doesn't come without challenges. There's a challenge with ammonia combustion, particularly if we look at the flame speed very low compared to other fuels, and also the ignition temperature very high compared to other fuels. And so this low flame speed and high ignition temperature means the combustion is not very easily happen, which could be good news because that means it's relatively safe to transport around as long as we don't make it leak. But then we need some energy to start with. And one method is to create some hydrogen ammonia mixture. And because hydrogen combustion is very fast. Another problem is that you have NOx emission. So this graph shows the amount of NOx and emission if you vary the mixture ratio. In the UK, there are a few groups working on combustion of ammonia, including the lab in Cardiff University. So I visited them earlier this year, and they say actually they prefer working with ammonia because once it's if you have a leakage, then you can smell it. While with hydrogen, you cannot smell it. And also the same volume, ammonia can last much longer than hydrogen. And if we use it as in a combustor, a combustor for jet engine, for example, then the problem of NOx is actually not so bad because the engine is quite long, so you can kind of, by varying the ratio of hydrogen, air, and ammonia, you can kind of remove that. But for internal combustion engine, those working on vehicles, then it's still a problem because the design of the engine doesn't allow the complete combustion. So we have those problems, and this is the areas that we are working on within the UK Hydrogen Research Hub. So we're developing Birmingham and UCL and also Cardiff are working on the novel burners, and then we are working on developing low-cost catalyst to crack ammonia, so to create that ammonia and hydrogen mixture, so facilitate the combustion, and then develop low-cost catalyst for removing NOx. So I think that's probably what I want to talk through. There are just so probably gave. I hope that I have given you a kind of a flavor of what are the research being developed in the UK. I think the UK has covered probably most of the necessary research areas that are needed to develop hydrogen technologies. So internationally, I think we are quite strong, but of course we need more funding. Okay, thank you.
Thank you, Professor. So Q&A, any questions?
Yes, please.
You covered a number of areas, applications for hydrogen, and you covered so much so quickly. I didn't quite understand what the process is for cracking nitrogen at the moment if you just want to produce hydrogen from it.
To crack nitrogen.
Yes, so you would talk about transporting nitrogen and then...
Ammonia, you mean?
Oh, sorry, ammonia,
Yeah.
I beg your pardon, ammonia. What's the current process for cracking ammonia to produce hydrogen?
It's a still thermochemical. So you have a catalyst, you put it in the reactor, then you have a increase. You heat the reactor up, and at probably 300 degree or 500 degrees C, then if ammonia need to be directly decomposed into nitrogen and hydrogen, this can come at 900 degrees C, but with a catalyst, this temperature can be lowered to probably 500 or 400 or 300 degrees C. So it's a kind of a standard thermochemical method.
So currently, is it used in commercial quantities, that process? Is it actually used to produce hydrogen from ammonia, or is that just, you know how to do it, but no one's done it in volume yet?
At the moment, so there are some ideas that some companies are thinking to probably produce ammonia in Middle East, where the abundance of solar energy, and they can run the electrolyzer for a long time, and so they can produce produce ammonia in Middle East and then transport to the UK as a hydrogen carrier and then crack the ammonia into hydrogen in the UK. But not all the people buy into this idea. So I have to say, what I'm showing you is some ideas, but not necessarily all the ideas are good ideas. Some people do not buy in this idea because they think thermodynamically. So you have to produce ammonia first. You have to input energy, and then you have to crack it, and you have to input energy again. So thermodynamically, you are losing energy there. But
yeah, but if you were using solar power, that's the problem. Because it's solar power, so you have an efficiency loss, so who cares?
Yes. Yeah, at least we can easily transport it across lands, where transporting hydrogen is difficult.
And has anyone considered using piping ammonia through the current gas network in the UK? Because that was what they're worried about.
I'm not sure in the UK, but I know in Russia, in US, they have ammonia pipelines.
Could existing gas pipelines be used without any modification? Because with hydrogen, it's a loss issue of that hydrogen escapes in gas pipes. But if you're using ammonia, would you have the same problem?
Good question. I'm not 100% sure. I think ammonia could have a bit of corrosive, being alkaline molecule. But I would think if it's plastic pipelines, it should be okay. Yeah.
Thank you.
Just a piece of information to follow on from that. Someone was attended a STEM in the Park event in Crawley on Saturday, and Metro Bus had their hydrogen-powered bus. Apparently they have a fleet of something like 32 buses. They get their hydrogen produced in the Middle East, liquefied and transported to the UK.
Yeah.
And they were trying to convince me that it was a profitable way of running a bus network.
Oh.
So there is an example of people trying to do that just now.
Thank you.
Add to that, there was a problem with the Crawley system, and that was the storage and health and safety.
Yeah.
The site they chose to put the hydrogen storage for loading up the buses at night was too close to population, and health and safety people said you can't use it. So currently the hydrogen buses in Crawley are not being used. So there's an extra problem with the Crawley buses. Can I ask another question? The question is slightly different, and that is, but it connects with the previous questions, and that is one of the problems in the grid itself is sometimes the wind blows, sometimes the sun shines,
Yeah.
and does hydrogen have any possible role locally? Generate hydrogen from solar or whatever, store it on site at the power stations, and then use it to generate during the times of dearth of solar or wind.
That's actually one of the ideas. I think I didn't go into detail, but one of the schematic actually showed this idea of using electricity from solar and wind and even nuclear to produce hydrogen, and then convert hydrogen back to power again.
Why isn't it happening? Is it too big investment or problems?
From my understanding, some companies are saying that because, as you say, the wind doesn't blow all the time and the sun doesn't shine all the time. So, if we look at the cost of where did I show the cost of electrolyzer? Yeah. So the cost of electrolyzer is affected by the load hours. Here, if of course, here it shows only probably a little bit of effect. This is the load, increasing full load hours from 3,200 to 4,200 hours. But they are saying that currently in the UK, the condition of the wind farm and the solar farm means that they cannot run the electrolyzer for a long time, because then, they don't have enough electricity. Then that means then for a lot of time the electricity are being put off, and this means this add on their capital cost. The fact that the electrolyzer are not running, not producing something, is adding on their capital cost. That's one thing. The other thing is how we store that produced hydrogen. I think that there are some research trying to look at maybe using the salt cavern as a storage base for storing hydrogen, but it's still being researched. And if we want to store them in the tanks, we have to compress them, and it's not very straightforward.
Okay.
Yeah.
I hope it does happen sometime. But
Yes, hopefully.
yeah.
For residential use, heating, cooking, that type of thing, there's been a couple of attempts in this country to have almost like an experimental village where they would actually...
Teesside.
This
Yes.
seems to be quite a move against it. I think people think it's dangerous, but surely town gas was a very, very high percentage of hydrogen anyway.
Exactly, yes.
So I don't quite understand why people are against introducing hydrogen into the current system. And if it were introduced into the current pipe system, would it leak any worse than it did in Victorian times and up to today?
Absolutely, it's a very good point. I think I don't know why, but I think probably because people now have high expectations on safety, maybe.
I think the press whenever they talk about hydrogen, the press always show you Hindenburg,
Uh-huh.
which is completely different.
Yeah. I mean, there are also a lot of accidents with batteries, with petrol-powered cars.
Yeah.
So I think yes, there's some safety concern, but it's similar to batteries and petrol. So we just need to learn how to manage them.
I think if petrol was invented today,
Mm-hmm.
we wouldn't put it in the hands of the general public. Quite dangerous stuff.
Yeah, okay, the last slide you showed, your father one,
Yeah.
two of the uprights were talking about catalysts, which seems to be a very important area.
I have to say, yeah,
Get to the end one.
because we haven't published the results.
Yeah.
So, and because this is being recorded, so that's the reason why I haven't put the details here.
Well, I'll still ask the question. It says University of Surrey.
Yes.
Is it that university that's working on these catalysts?
We are working on the catalyst.
What, the UK?
Yeah, we are working on, my group are working on the catalyst.
And how does that relate to the rest of the world? Because presumably it's a pretty key area, this.
It is,
It's
it
interesting
is.
what you just said, that you're worried about it being published in too much detail and so on.
Mm-hmm.
So does that hamper your research and so on? Because it's a jolly sensitive and valuable area.
Mm.
And how much information can you exchange, and how many patents do you take out, etc., etc.?
It's probably too early to say to file patents because we just started working on this 1.5 years ago. So we still need to test those catalysts to confirm that they are highly efficient. So far, they are working very well for converting NOx into nitrogen, but we need to confirm whether there's any trace of N2O. So for converting NO and NO2, it's no problem, but we need to still confirm whether they are also very effective in converting N2O, because N2O is also a greenhouse gas, and normally it's only traces of that in the gas emissions. So yeah, we need to make sure that they do work very well before we can file patents.
And if they do work well, could it be a real winner for the UK?
We'd like to hope so, but I think it's a very competitive world. So I am not sure. Yeah.
Well, another question, if I may. Early on, you had a slide. You were talking about social
Acceptance.
Acceptance of
Mm-hmm.
hydrogen.
Yeah.
And I remember as a boy being scared. If I saw a lorry with hydrogen cylinders, I initially thought hydrogen bomb. I don't think that now. But I was at a talk the other day, a lot of engineers, car engineers, and they were pushing forward the same point, that the public are scared of just the word hydrogen because of its nuclear annotation. So was that one aspect of what you were worried about, or was it more to do with these other things, talking about danger and escaping and so on? There was one chap working on social aspects or something, remember?
Yes, Chris Jones at Portsmouth University. You may want to also get him to speak about hydrogen acceptance, social acceptance. I think it's at the beginning. He's very good. He's very good at this.
Yeah, there he is.
Yeah. So I think, as you say, I think we all see there's a barrier in public acceptance, and so what Chris is doing is he's trying to understand where those barriers come from, and how we could try to break those barriers. Yeah, so he's doing a lot of, he's a social scientist, so he's doing a lot of survey and doing a lot of research, trying to understand those, and then hopefully we know how we could break those barriers.
One more. Going back to your catalyzers, I understood about the current density regarding the efficiency of output. What's the function of voltage? Why is it a problem if voltage is high or low?
Okay. So the current density, according to Faraday's law, will basically dictate the amount of hydrogen you can produce. So current density is directly related to how much hydrogen you can produce. Then at that same current density, the voltage, so I should have shown a kind of voltage current curve for electrolyzer. Normally you expect when you increase current density and you have an increase of voltage. Now, for different electrolyzers, if you operate at the same current density, say 1 ampere per centimeter square, then they can be operated at different voltage. That means for alkaline electrolyzer, for example, it typically operates at a higher voltage. That means to produce the same amount of hydrogen, you need a bigger amount of electricity as input. So it's beneficial to be able to operate at a high current density, but low voltage.
So in practice, are these electrolyzers connected in series, so they're like a big battery? So you've got, say, apply 50 volts across it because you've got 40 electrolyzers in series. Is that how it's done?
You can tune this, so you can play with this. You can either place them as in series or in parallel. You can play with this. Mm-hmm. But in general, we want them to operate at a high current density. So the PAM one can operate. Yeah, people have demonstrated up to 3 ampere per centimeter square, where the solid oxide one, people have shown probably 1.5 ampere per centimeter square, and our next exchange membrane one also can operate at high temperature. No, sorry, high current density, because those are all based on thin film technology. So each layer in the electrolyzer are very thin, a few hundred micrometer. That's why that then make the internal resistance very low. It lowers the internal resistance. So according to the electrochemical thermodynamic principle, the current is being used to generate hydrogen. But then if we have a higher resistance, means we need a higher amount of electricity to overcome those resistance. So you need a higher amount of electricity to come in. Yeah.
Any other questions?
And
Okay.
I think I have the tendency to try to show a lot, but assuming that people understand the background. I apologize for that. But yeah, do feel free to ask questions if I didn't make a point clear.
Can I ask one more?
Yes.
Going back to white hydrogen,
Uh-huh.
the article I read about it said that it actually regenerates somewhere deep down. So it's constantly being produced. So it does sound quite exciting, but I suppose what you're saying is it's not really in commercial quantities yet or ever.
I think I saw from the news, so I'm not very familiar with this. I haven't done a lot of research into white hydrogen, but from what I saw, some companies did some kind of techno-economic analysis. So basically we call TA, is to evaluate whether a technology would be economically viable. they say this it could be economically viable. It's just I think you need a lot of care to do that to bring that hydrogen up. And it's I guess it's more difficult than digging the oil up.
You run into the fracking lobby or something.
Yes, and also to transport that hydrogen. Yeah, I think U.S. They discovered a lot of wet hydrogen reserve, and I think they are very in favor of digging this up and then transport in pipelines. But the UK so far haven't found any wet hydrogen resource.
Right. Thank you, Professor.
Okay, you're welcome.
Sure.